right, in this video we're going to look at the null space of a matrix and think about describing it geometrically and think about finding a basis for it. So I've put a couple of matrices up here that we're going to just use for our examples, and just notice that I kind of made them different dimensions just to provide a little bit of contrast between the couple of examples. All right, so the first thing that we're going to do is just use the definition of null space to write down what is the null space of these matrices. And when I do that, I'm going to think a little bit about what those symbols mean that I'm writing down. All right, so definition of a null space. So null space of the matrix B is the notation I'm using here. Null space of the matrix B. So the definition of that is that it's the set of all vectors such that this matrix times the vector gives you the zero vector. So you have to pay a little bit of attention to dimension, maybe. This is a 2 by 2 matrix. So if I think about this matrix times a vector, that would have to be a 2 by 1 vector for this one. So I'm just going to use x and y for my entries. Really, you could use whatever letters you want. But I'm going to use x and y also to kind of help provide a little bit of connection to some geometry so we can sort of think about what this might mean geometrically. But just an arbitrary 2 by 1 matrix such that this matrix times my vector is the zero vector. That's just the definition. Every time you're asked about a null space, thinking about that definition is the set of all vectors such that the matrix times the vector gives the zero vector. So the word null is about zero. So this is where the zero comes into that definition. All right, so at that point I've written down the null space. The next question might be, do you understand geometrically what this is, or can you describe it? So I'm going to do a little kind of scratch work below this definition to think about describing it. All right, so my first step, usually when I want to do this, is to go ahead and do this matrix multiplication that we have right here. And then maybe think about that essentially I'm going to end up here with a system of equations when I do that. So you might write out a few more steps than I'm going to write out just to save some space here. But I'm going to go ahead and do the matrix multiplication. So I'll have 2 times x plus 4 times y. So 2x plus 4y. And that's going to be the first entry in my matrix when I do the multiplication. But because that's going to be equal to this vector over here, the first entry in the result of this is going to have to equal the first entry here. So I'm going to go ahead and just take it out of matrix notation and write just equals 0. So top entry from this multiplication is going to have to be 0. And then the bottom entry, when I do this matrix multiplication, I'll have 5 times x minus 1 times y. So 5x minus y. And that's going to have to equal this entry here. So 0. So what I have here is a little system of equations. We know how to solve systems of equations, so solve it however you want. This one's pretty easy to solve by hand, substitution or elimination. If it's more complicated, you can use a matrix or a calculator to help you solve this system. So whatever you do to solve this system, when you do this one, maybe you can think a little bit about it. It's not too hard to solve. But you're going to get as the only solution x equals 0 and y equals 0 is the only solution. All right, so I used the letters x and y here in my vector to emphasize some things about connections to geometry, to help us think a little bit about this vector space, and thinking a little bit about the geometry of it can help us when we think about finding a basis for this vector space. So you would not necessarily have had to use the letters x and y, but if you do, it maybe helps you think a little bit about the xy plane. So notice that this is a vector in R2. So in the xy plane, maybe I think about drawing an xy plane, but it's not all vectors in R2, right? So when I write down this definition, if I have a 2 by 1 vector, that's a vector in R2. But then thinking about which vectors actually we're describing depends on solving this system of equations. So depending on the system of equations, maybe you get a unique solution, maybe you get infinitely many solutions. These ones for null space won't ever have no solution. They will always have a solution at least. And if you just think about this matrix multiplication, I'm thinking about vectors that multiply times a matrix and give me the 0 vector. The 0 vector is always going to work here. When x and y are 0, that's always going to work. So when you think about null spaces and think about them geometrically, just remembering that when all the entries are 0, that's always going to work, right? The question maybe is, are there more that would work, right? So since these are always 0 for thinking about null space, it's always going to work when you have all the variables being 0 here. Okay, so in this instance though, my only solution is when x and y are 0. Geometrically, I might think about that as just a point at the origin, or maybe we think about that as the 0 vector. All right, so here I've written down the null space, and then this work here was trying to help me kind of describe it geometrically. We're going to come back and think about finding a basis for this null space also. But I want to do the same work that I've done here for this other matrix, and we'll get that far, and then we'll think about a basis for each of them. All right, so again, thinking about just using that definition to write down what a null space is, I need to pay a little bit of attention to dimension. This is 3 by 3, right? So the null space of this matrix C is going to have to be a 3 by 1 matrix. So I'm going to use x, y, and z. You could use whatever variables you want there, but some set of vectors such that this matrix times the vector that I wrote down is equal to the 0 vector. So null means 0, something to do with 0. All right, so that is just using the definition of null space to write down the null space. So if you're just asked to write it down, I guess really you could stop there. But probably I will ask my students to describe it geometrically so that I can be sure you understand what's going on with this null space here. All right, so I'm going to do the same thing over here that I did with the first example. I'm just going to write down the matrix multiplication, and I'm going to take that out of matrix notation so I can just kind of think about the little system of equations that would result from that. So top row times this vector, so 2 times x plus 3 times y plus 0 times z. It's going to be 2x plus 3y, and that will have to equal this first entry in my 0 vector here. And then same thing with the other rows, so 4x plus 6y plus 0 times z equals 0. And then for the bottom row, I'll have 0x plus 0y plus 1z, so just z is equal to 0. Okay, and I want to think about this geometrically. So these vectors that I'm working with here are in R3, right? They have 3 entries. So geometrically, if I want to think about that, I'm thinking about R3, so x, y, z coordinate system. For too much beyond 3 dimensions, maybe drawing the pictures starts to become more complicated, and you have to go back and think about these maybe more algebraically. But since we're in R2 and R3, we're going to leverage that here and think about the geometry. All right, so I constructed this matrix intentionally so it was pretty easy to see kind of what was going on. But whenever you do this step, no matter what kind of matrix you start with, you're going to get a system of equations here. And maybe you want to do a little work solving that system of equations to think about what the solutions are for that system of equations. For this one, I made this problem so it's pretty easy to see just for this video so that we don't have to do that solving the system. For this one, you can see here that z is restricted to 0. So z must be 0, but x and y, I've got a free variable here. So you could do some row reduction on a matrix and see that or whatever. But z must be 0. So geometrically, that means that my null space is in the xy plane, right? In the xy plane. Although we're talking about these overall vectors being in R3, it's not necessarily every vector in R3. So for this null space, these vectors, since z is restricted to 0, are going to have to be in the xy plane, where z is 0. And then I also constructed it so that these other two equations, it's pretty easy to see just by looking at them without necessarily doing any extra algebra, that these are really the same equation, right? I've just multiplied the top equation through by 2 to get the bottom equation here. So because those are the same equation, they're really giving me the same piece of information about the relationship between x and y. And however you want to think about that, 2x plus 3y equals 0, or 4x plus 6y equals 0, or if you're thinking about it graphically, sometimes students like to solve for y, so they can think about drawing things like that. So whatever way you want to rearrange these variables, as long as you're using correct algebra to do that, you should get the same representation when you draw a picture of that. So I'm going to just solve for y in this first equation. So I'll get y equals negative 2/3 x. Okay, so y equals negative 2/3 x. If I want to draw that on my xyz coordinate system, remember we're going to be down here in the xy plane. There's a lot of ways you could think about doing that. I'm going to just think about in terms of like slope in the xy plane and rise and run. Maybe have to be a little bit careful so that you're making sure you plot things correctly so that since your y-axis is going this way and your x-axis is going that way. So if I think about this in the xy plane and sort of slope and rise and run, the rise would be -2, so that would be in the y direction. So 2 down the y-axis, or in the negative direction of the y-axis. And then the run would be 3, so 3 in the direction of the positive x-axis. So I'm not going to scale this off to make this perfect, but essentially I counted -2 in the y direction and +3 in the x direction. You can also think about just picking a number for x, like 3 works nicely. So when x is 3, you get y equals -2, and I end up kind of here at the same point. So -2 in the y direction and 3 in the x direction. And again, I didn't scale that off to make that perfect. I'm just kind of going for a little sketch here to think about that. Okay, so geometrically, what this is really a line. It's that line in the xy plane. Every value that satisfies this system of equations is going to be on that line in the xy plane. Really, when we think about the null space, we're talking about all vectors along that line in the xy plane, but extending in each direction. Ooh, I'm running out of ink here. Extending in each direction, right? So we've got that line, y equals -2/3 x, not -2x, that's not a line. -2/3 x that's in the xy plane. So describing that geometrically, either in words or with a picture. Maybe if you're only going to use the picture, maybe you make it better by scaling some things off so it's clear. All right, so at this point, I have used the definition of the null space to write down the null space for each of these matrices. And then I did a little bit of work with the resulting system of equations to think about them geometrically. Part of the goal for us, though, will also be to then be able to write down a basis for that null space. So I want to use kind of what I've got here already, thinking about them geometrically, to be able to write down a basis for each of these null spaces. So a couple of things to remember about a basis. So a basis is a set of linearly independent vectors that can be used to generate everything in the null space, or in the space that you're working with, in this case, null space. The other thing about a basis is that the dimension is the number of vectors in any basis. Right? So dimension is the number of vectors in any basis, and there could be more than one basis for any vector space. So there's a lot of ideas to connect there. And the goal would be to leverage whatever parts of those ideas are relevant to the piece of it you're thinking about to be able to write down a basis. But we want to be able to write down a basis for this null space and a basis for this null space. Okay, so let's start with this one here. So we really just have the point 0, 0. This null space, in other words, really is just the 0 vector. Geometrically, we're thinking about the point, but if I kind of go back here to think about this, in this case, this null space really is just the set containing the 0 vector. I'll just write that in kind of shorthand notation here. Just the 0 vector in this case, or the point at the origin. So if I think about a linearly independent set of vectors that generates all of this, well, there's not much to generate, right? It's just the 0 vector. And so sometimes students will write down, don't stop the video when I write this down because it's not correct, but sometimes students will write down just the 0 vector, right? Because they'll say, well, it's just the 0 vector. But when you go back and think about the ideas about dimension and linear independence, either of those two things should tell you, oh, wait, that's not quite right. So let's talk about linear independence. Any set containing the 0 vector is not linearly independent. You can go back to the definition of linear independence and see why that's true. But any set containing the 0 vector is not linearly independent. So when you're writing down a basis, if one of the vectors that you've written down is the 0 vector, that's not okay. You don't have a linearly independent set. So that's not a correct answer for basis. The other connection, which maybe if you think about this thing I'm going to mention first, maybe helps you write down your answer for a basis right away without thinking through too many other things, is to remember that the dimension of the space tells you about the number of vectors in any basis. All right, so geometrically, these vectors are in R2, but we're not using all of R2. R2 itself, if we're talking about all of R2, is a two-dimensional space. But this space is not all of R2. It's just this single point in R2. And if you think back to geometry, a long, long time ago for some of you, but geometry, a point is 0-dimensional. Right? I don't have any directions I can go from that point. A point itself is 0-dimensional. So if you remember that from geometry, or make that geometry connection, drag that back out of your memory, that a point is 0-dimensional, that tells you that any basis for this vector space contains 0 vectors. So there is not really a basis for this vector space. Or you could say the basis, I guess, is the empty set. But there is no basis to write down for this vector space. All right, let's look at this one. We do have vectors to write down here. All right, so for this one, I'm going to start by thinking about the geometry. So geometrically, these vectors are living in R3, right, in this three-dimensional world, XYZ coordinate system. But it's not all the vectors in R3. It's only the vectors that are on this line. And when you think about a line, maybe you remember, or maybe you can just recall by thinking about it a little bit, looking at this picture. When you're on a line, you can go one direction or the other direction. That's one direction of motion, right? I can't go forward and backward off that line or up and down off that line. I can just go one way or the other along that line. So a line is one-dimensional. Maybe you remember that from geometry. A line is one-dimensional. So that tells me that a basis is going to contain any one vector, linearly independent vector, that generates this whole line. So I have a lot of choices here, but I'm going to write down one vector that can be used to generate everything along this line. And as long as what I write down is not the 0 vector, then and what I write down, I guess, is on the line, then I have a correct basis for this line, for this null space. So there's a lot of ways you can do that. Some students will look at these equations and say, all right, I'm just going to pick maybe a value for x, like 1, and then y is going to be -2/3, and then remembering that we're in the xy plane, z has to be 0. So that works. It depends what you're going to do with this basis. Maybe you don't want to work with fractions, so maybe you would prefer to have whole numbers or integers in your basis vector. So really any non-zero scalar multiple of this vector would also work. So if I just think about multiplying this vector by 3, that clears the fractions, and so I could have 3, -2, 0. So that works. So really any non-zero vector that is along this line works, and I can generate this entire null space by taking scalar multiples of this. The other thing that you sometimes may want to do with a basis is perhaps make this into a unit vector. We won't do that for our purposes in this class, but sometimes that might be something too. You should hopefully remember from when you began working with vectors how you can rescale a vector to make it a unit vector. So if you wanted to do that, you could do that. For our purposes, we'd probably prefer clean numbers to work with. You might notice the magnitude of this vector is square root of 13. Makes it a little bit more difficult to work with if you rescale it to be a unit vector for what we will be doing. But if you take linear algebra, there will be times where you want to make a unit vector. So any non-zero multiple of this vector works. Okay, so a lot we did here. Use definition of null space, think about the geometry, and then use that thinking about the geometry to find a basis for the null space. Make sure you do some practice of this. There's a lot going on here. Each individual concept isn't hard, but it can be difficult to pull it all together. So make sure you have this pulled together before you kind of look at the next topic. In the next video, I'm going to use these same matrices, and we're going to do essentially the same kinds of process, but with the column space of each matrix. All right, so think about null space for a while, and then check out that other video.